teleoperated, but we cannot have an accident with this. Even if you try, you cannot, because there is some polygons where it's forbidden to go, another robot, and as soon as you make something dangerous, then he becomes autonomous. But normally it is totally teleoperated, so impossible to have an accident. Normally, if no bugs. Okay. Good. So today I will speak about dynamical system. So what is, for us, what is a dynamical system? A dynamical system is something of the form x dot equal f of x. So we can assume here that it is autonomous. But now, due to uncertainty, sometimes we prefer to represent like this: x dot belongs to a set f which depend on x. So what is the difference? It means that in a state space, so the state of a robot is its position, orientation, speed, and so on. Here you have one possible direction for x dot. Okay. But in this case, you have many different, you have a set of possible evolution for x, which is here, and this corresponds to f of x. Okay. So here we'll try to prove some properties to have guaranteed method for both of them. It's very similar, the same method, the same kind of methods. So how did we start it for this, for the security of robots? We started building 10 years ago some robots like this one, the sailboat robots, and the objective was to cross the Atlantic Ocean, to be the first. So we're very motivated, very. So the first one, and especially we were motivated since we succeeded to cross for 3 hours La Rade de Brest. So Brest is in France, Brittany, west part, and we succeeded. So it was we were very motivated. But each time, we tried maybe 5 or 6 times. We tried to cross the Atlantic Ocean with different boats. Each time, of course, we failed because something has broken. So it's difficult to cross. And other school in Brest, for instance, here it's l'École Navale, a military school. They try also with stronger boat, and everybody has failed up to now. Okay, so it's a problem. It's more, we don't know why. Sometimes when it breaks, we don't know why, but we have to. So we made some very small boat. We made VEMOS with Ifremer. So this is VEMOS. And then we started to develop method, not to cross the Atlantic Ocean, but to collect measurements. So VEMOS is here. We saw yesterday some videos. And it is an autonomous system. As soon as you have a controller, you have an autonomous system. So at this moment, even if normally you have this, for simplicity, I will assume that I have this. Okay, but it's the same for the method we'll propose. Okay, so the controller for VEMOS is based on line following. It means you give A, you give B, you have a line, and you want to stay in a corridor of something like 50 meters around the line. And we want to prove that VEMOS will stay inside the corridor, but not that here it is a hybrid system, not exactly this, even if I assume here that it is a hybrid system, mainly because of the sail. And we have some, because of the wind, we have some time to change tack often to go upwind. So it is a hybrid system with a controller, and we want to prove that this system, which is not so simple, will stay inside the corridor. This is the controller we used. So the controller is as simple as possible because we have to prove some properties. but you can see it is not as simple as this. So here you have the output of the controller is the angle of the rudder, the length of the main sheet for the sail, so the output. Here it's, and as an input, you give A and B, the line you want to follow, and some sensors. So what are the sensors in VMOS? GPS will give you your position, the heading, the speed or the wind here. And this is an algorithm with a cosine function, trigonometric function, and totally nonlinear. But we have to prove properties with the sailboat plus the controller. Okay, so how we can validate such a dynamical system to prove that it will stay inside the corridor? What is done classically is by simulation. So 3D visualization, we have some, we show that for all initial conditions, you will maneuver so that you will follow the line, but it's not a proof. Okay, it's not. So we need a theoretical validation. So when you have this kind of thing, it's a differential equation. You can transform this problem into inequalities without derivative. From this to this, you need what we call in control theory a Lyapunov approach. So more than 100 years ago, Lyapunov has proposed some methods to go from one differential equation to an inequality. Okay, so the Lyapunov approach, it tells you, so it's been proposed for stability. First, you need to find some kind of Lyapunov function, which is not easy to find. It means you can go from here to here, but you need intuition. Without intuition, you can do a solver which do it automatically. So you have something that, some kind of energy function, which tells you that if this energy function always is always negative, except when you are 0, you will converge to 0. Okay, very. So we use some kind of similar approach. It means you are in the safe space, and you have a set like this, where here V is negative, here V equals 0, here V is positive. A Lyapunov approach in this context tells you, if I am here outside this set, then V will decrease. So it means you have a lot like this, and since you decrease, you will go in this direction, and one day you will enter in this set. So when you are positive, this function should decrease. You will enter in this set. But once you are in this set, you can do what you want. There is no condition when you are negative. So this corresponds to a constraint satisfaction problem, because this, thanks to this, you can transform into inequality. So the inequality I try to represent here, V equals 0, V negative, V positive. You will decrease, but once you are here, you can converge to limit cycle, whatever. So you have some kind of theorem, quite easy to prove. If you have this set of inequalities, this corresponds to V dot. If this set of inequality is inconsistent, then you will converge to this set, and once you are here, you will stay there forever. The problem is to find the function V, but for practical problem, we have a good intuition. We'll spend a lot of time on this, and we have a tool, a Lyapunov tool, which makes us possible to prove some properties. Okay. So once we have done this in a robotic community, it's not sufficient. We need to have experimental validation. It's always the case here. So we made this kind of square spiral like this. For sailboat, we use this kind of thing, of pattern. And in red, it is what you want to do. And in green, it is what VMOS has actually done. So the robot made this trajectory. So this is something like 5 kilometers. And we can see that due to the validation, we have a specific behavior of VMOS, and we stay inside the corridor. We stay here for something like half an hour, that's why you have plenty of things, and we came back to the harbor. Okay, so take care, in green, it was VMOS has actually done. Okay, so in fact, the fact to try to prove properties makes some controller that have not the same track as other controller. You can see that it is very geometrical. Okay, but it's important to stay inside the corridor, so you can ask a supervisor. The robot can ask a supervisor, I want to reserve this corridor for me, so I am, please ask other boats not to come inside, and you start to have some rules like the traffic rules we have for cars, and we are able to deal with many robots. Moreover, what we want for boats with motors, we do not want only to stay inside a corridor, but we want to stay inside a bubble. So if you have many robots in a small area, everybody has to stay inside a bubble. Okay, so another validation was Brest-Douarnenez. We started in Brest with VMOS. So something like 3 hours later, outside the Goulet de Brest, we met a submarine. So this one, so military submarines, many in Brest. So it's me, so I had to catch the boat. So it's not autonomous anymore for a while, because this one wanted to fire our robot, because it was not he got directly to the submarine. So he came back from 3 months under the water, he came back here, and he was not happy to see such a robot. Okay. Later, it was at night, because at the beginning, and tomorrow morning, it was Douarnenez, small, and it is a track it has actually done by VMOS. So it's a zoom out. So if you zoom in, you will have here plenty of zigzag, of course. Okay. And of course, yesterday I showed you a video with VMOS, and it is a track it has already done to survey a zone. And when you see triangle like this, it means that you have the captain of the boat that tells us, I will catch the boat here. So you ask the boat to do triangle and triangle. So maybe 10 times he has done this. And why he put a square here? Because he changed his mind. Oh, it's better if I go here, something like 15 kilometers from here. So I will catch the boat here. So that's why he made squares like this. Okay, you understand that. So now, the problem with Lyapunov method is you need to have a lot of intuition. It is the case if you have a sailboat. But when you have a general system, it cannot work. You have no intuition, like a Van der Pol system. You have no intuition of how it... So I will deal with a specific example, and it is what I call a Eulerian state estimation. So normally, what we call as a state estimation problem, we have here, okay. So if I deal with a state estimation problem, classical state estimation problem, you have a system like this, and you have some measurements at time ti. I am able to make some measurements of the state of x. So if you want, this can be, so at time, I know ti. I know the time instant at which I make the measurements. This can be replaced, if you want, by x of t belongs to a set xe. This is equivalent to say this on this. But I know ti. So it is what we can call a Eulerian state estimation, because ti is known. Lagrangian state estimation, what is called a Eulerian state estimation is different. So I will try to explain two approaches to deal with state estimation. So it is we have on this picture, when you have a differential equation such as this one, you can, at x, you have some direction like this, which corresponds to x dot. So when you have to have a good understanding of the differential equation, geometrically, you can take a point and to follow it. And you get a trajectory, and it is what is represented here by the leaves. You follow the leaf, they move, and when you see the leaf moving, you have an idea of the wind. The wind corresponds to this. There is another way to see geometrically how behave your differential equation is you look at the flags. Just looking at the flags, you will be able to have an idea of the behavior of the fluid, and you obtain an Eulerian approach. So, Eulerian approach with the flags, a Lagrangian approach with the leaves that move with the fluid. Flags don't move with the fluid. You understand the two approaches? So, when you deal with this one will be more geometrical, and this one will require some guaranteed integration when you deal with guaranteed method. We don't want to use this one here, more Eulerian approach to avoid to follow the fluid. Because when you follow this, you have to integrate with Runge-Kutta method or an interval counterpart. So what is an Eulerian state estimation? You don't see the time anymore. You have a differential equation, and you have some sets. For instance, a set here, x1. You have a set x2. And you know that for some ti, but you don't care about ti, you have visited this one. You have visited this one, then you have visited this one, so there is an order. I know that I have visited x1 before x2. Okay, so I have visited some sets, and there is an order. Sometimes there is order, sometimes there is not. You understand what is a... So when you want to check, some properties, you want to show, for instance, that you have never visited x1. It is still a Eulerian state estimation because it's forbidden to go here. Okay, so you search for trajectories. Everything is based on the notion of invariant sets. What is an invariant set? I have shown before an invariant set. It is a set, so I erase move this. When you deal with a differential equation like this one, an invariant set is a set like this. This set is said to be invariant with respect to this differential equation if once I am here in the set, I will stay there forever. I will never go out. In this case, I say that this one is an invariant set. Positive invariant set, because in the future. Maybe in the past, I come from outside. But in the future, never this happens. Geometrically, it can be seen with the Eulerian approach. The vector field enter inside. You never have such a thing. If you have such a thing, you may have some points that go out, and it means that it is not a positive invariant set. Okay? So I define something like a flow function, which is able to tell you that if I am here, I will be here in the future corresponding to t, t, the future. So I have some kind, I will use this notation, but of course, I don't have an analytical expression for this one. So it is what I have defined. A set is positive invariant. If I am inside, in the future, I will stay inside. This corresponds to A in this definition. What it can easily be proved, and you can understand it geometrically, if A is positive invariant. If B is positive invariant, do you think that the intersection of the two is positive invariant or not? Yes? Logical? Yes, of course. If A is positive invariant, is B is positive invariant, do you think that A union B is positive invariant? Yes? For everybody? Yeah. Okay. So it means that it is a lattice. It is a lattice with respect to the inclusion. The set of invariant set, since it is a lattice, the notion of largest positive invariant set included. So if I have a set X, like this, a big set, X, if I take the union of all positive invariant set, there exists a union of all, it will be a big set like this. It may be the whole space, but maybe not, because some point here may go outside.
Well, if you take the whole space, I can
No,
go
inside. The notion of largest positive invariant set containing X, this notion exists due to the fact that the union of two is positive. So, in fact, since it exists and it is unique, I will be able to find some algorithm to find it. So I will explain later. But this largest positive is a set of all initial conditions, so that I will stay in X forever. So we have some tools based on interval analysis, which makes us possible to find an inner and an outer approximation for the positive invariant set. So I will give you an explanation here on an example. It is a Van der Pol system, a system classical in dynamical system with a limit cycle. You have this one, and you can see here some arrows, like this, like this, like this. Okay. Do you think that this point, this is X, do you think that this point belongs to the largest positive invariant set inside X? This point. You follow the row, I go outside, so this point does not belong to the largest positive invariant set. This point, it belongs to the largest positive invariant set. I will check, I follow the rows, and I converge to the cycle. Yes. So this point belongs to the largest positive invariant set. So if I use a tool I will explain later, I am able to find an inner and outer approximation of the largest positive invariant set included in X. If I am here in blue, I will leave X. If I am in the magenta, I will stay in the magenta forever. It's okay?
What are these other regions with gray?
These cones. Yeah. This cone corresponds. There is boxes. Here it's difficult to see, but there is many boxes, and corresponds to f of x inside the. Okay. So of course, if I reverse time, I obtain the negative invariant set. No, it's a set of all points such that in the past, I stay inside X. Not in the future, in the past. So it's very similar, except that I have to replace f by minus f. So if I follow X, I go to the future. If I follow minus f, I go in the past. Okay, so it's very similar, positive invariant set. So what I want to show here, it corresponds to the largest negative. So let me explain. If I am here, I will converge here. So, but if I am here and I go to the past, I will go out from X. But if I am inside, if I go in the past, so in the past, let me say, I will converge here. So if it corresponds to the inner and an outer approximation of the largest negative invariant set. So we can see here that this kind of tool will make me possible to find limit cycles. So what we call an invariant set, it corresponds, you need to be both positive and both negative. So it corresponds to the limit cycle. It means that the set, in this kind of set, the field is tangent. So I make the intersection between the positive and negative invariant set, and I will obtain the largest invariant set. So in our context, okay, I will. So what we call now the forward rich set. I have a set like this. So I would just want to show you that everything, a lot of things, can be cast into the framework of a positive invariant set. So what is a forward rich set? I have a set X like this. I have a set X. And I want to find, so it is a set X. And I want to find the set of all X such that there exists, so for instance here, such that there exists a T and there exists a X0, for instance this one, such that, so here for T, I reach X. So it corresponds to the future of this set. The future of this set. So this corresponds to the forward of X with respect to the function f. This forward rich set is something important in control because it's important to have an inner and an outer approximation. Why an inner? Because you know that these points you can reach it. Why an outer? Because this point you know that you will never reach it. So it means that if you have a forbidden region here, if the forward rich set do not intersect this one, it means that your system is safe. Okay, so the forward rich set can be expressed in terms of forward rich set. So how can I do this? Of invariant set. So I take this one, I take the complementary of this one. So if I take if I take forward of f x and the complementary, it corresponds to the set of all x such that for all t positive, so the complementary, for all x, for all, so this one I can transform into phi belongs to x. Belongs to x0. Okay, so what I have done here, I have replaced f by minus f by inverting s0 at x. This one I have replaced the existence by belongs to x, and I have obtained that this is equivalent to compute a positive invariant set.
Yeah. If instead of a differential equation, you have a differential inclusion, do you still have?
Yes, I have this kind of thing. Okay. Yeah, I can. So, just an explanation I have shown yesterday. Let me check. Yes, good. So, here you have a notion of forward rich set. If my state is here, I am able to compute using invariant tools that the future will be inside with an inner and an outer approximation. I have shown this yesterday. Okay, I have also the backward rich set, which corresponds to all points that will reach in the future my box. And now I want to explain how we compute actually a positive invariant set. So everything is based on the notion of maze. So if I have an uncertain real number, if it is uncertain, I can represent by a set, which is an interval. Quite classical. If I have a vector, I can represent by a box or by polygons. So this one is called a domain for the vector. Now, here, when I deal with differential equation, I deal with path. So a path is, this corresponds to a path. It's not like a trajectory, because you don't have the time. The path is only the set in the image space, also in the, it corresponds to, you don't have the time anymore. So it's a path. So maze enclose a path. It is a set of paths, a domain for a path. So I show you geometrically how it works. Here you have a path, the origin and a path. You don't know where is time, but there is an orientation. You don't know if you go fast and slow. You just know that you go in this direction. This is a path. If you want to represent inside the machine a set of paths, you can use, for instance, a paving and a road like this. So here you have the path, and it belongs to what I can call a maze. So it means that this path is possible, it's consistent with the rows, but if I take this and I come back, it's not possible because I have no row from here and here. So I have the set of paths that are consistent with the maze, and some others are not. So I have a way to represent inside the machine a set of paths. This path belongs to this set of paths. It's okay for you? But, yeah.
How was that something? How did you decide how to
Up to now, it's a formalism. I do not decide yet. There is no algorithm. Just, it is a set of paths. You should understand this. Now, it is not the one we use. What we use is this maze. You have a paving, and you have doors. Instead of rows, I have doors. So doors is like this, open, close, but you cannot go like here. So this path, to be consistent with this maze, has to cross doors, but cannot cross here. It should cross here, and here, and here, and this path belongs to this set of paths. So what is a maze for us? It's a paving plus the doors. But most of the time, we represent polygons, convex polygons, to have a better idea, a better view of how it works. But in the machine, we memorize the paving and the doors. So what is a maze? It's a paving and doors between two adjacent boxes. This maze is included in this maze. Do you understand this? This maze is included in this one. Why? Because if I take a path in this maze, for instance, a path, it also belongs to this one. But if I take a path in this one, for instance, it's difficult to say, but for instance, this one, it is not consistent with this path. So this one has more path than this one. There is an inclusion. So it can be seen as an interval of paths. I can make the union of two mazes, the intersection of two mazes, the set of mazes as a lattice structure. I can compute with mazes. So I will be able to develop, so I try to go fast, I cannot explain everything, but I am able to define some contractors on structure that are more complex than boxes and intervals. So I can define contractors on mazes. So let me explain a few of them, just to show a representation. I have a box, so sorry for I have a box like this, and I have a part of maze, doors, input doors, output door. These arrows that are uncertain are represented geometrically in the picture by a cone. I take all arrows, I put this from the same origin, and I obtain what I call a cone. This cone is obtained using interval analysis, so it's guaranteed. From this cone, which corresponds to some inequalities, I am able to contract the polygon. okay, I cannot go here if I follow the cone, because I have to enter here. I can do this, but I cannot do this if I want to respect the cone. So I can contract the polygon, but also I can contract the doors. It means if I follow this, I cannot enter here and go out here because I have to follow these directions. So I can see that what we call a flow contractor, I have to be consistent with my differential equation or my differential inclusion, and I obtain a contractor. So let me show geometrically how it works to avoid mathematics. This one is a forbidden zone. I don't want to go inside this zone. So of course, if I am here, can I avoid the forbidden zone? I try to find path that never go here. If I start from here, do you think I can avoid this forbidden zone? Yes or no? No, I cannot, because I can do whatever. I will go here. So I eliminate this one. I eliminate this one. I eliminate this one. Due to this internal structure, I cannot eliminate this one because I represent a convex set in my structure. But so after I am able to eliminate this one, and this point after will go to here, but this one will go to the forbidden zone. Even go through here or here, but this one I will propagate backward and obtain some points that will go to the forbidden zone. So the path I'm searching that will never reach this box is here. So it means that I have some kind of outer approximation of the set of points that will never reach the forbidden zone. It looks like, if you look, it depends how you see. But if I am here, I'm searching for a path that will never reach this one. So this path cannot be here. So in the set of paths I want to search, no one is here, so I have an outer approximation. It depends how you see things. I can do also the same. Start from here, and I'm searching for an inner approximation. So it means that if I am here, maybe I will go here. I cannot decide. Maybe I will go here. This one, we don't know yet, but maybe I will go here. So I will not be able to prove that this point will never go there. And I propagate backward, and I'm not able to prove that this one will never go here. But once I go to the reach point, to the fixed point, I have a theorem that tells me that once I have reached the fixed point, I have a proof that this one will never go here. Okay, so it's important. But to have an interpretation, I have to go up to the fixed point. Otherwise, at each step, I cannot prove anything on this. So I will try to come back on the Eulerian filter to explain how it works. Okay, yeah. Okay, don't worry about it. So I have to visit, I try to find for a path that visit this one and this one and this one, a set of visit sets. I have to respect the order. So the principle is as follows. Assume that at time k, I have all points inside xk that had visited xk minus 1, xk minus 2, and so on. And I want to do the same here. So first, I compute the forward reach set with respect to this one, and I know that this corresponds to the future of consistent point. Then I will do the intersection with this one, and I have here the set of all points that have visited this one and this one, so xk, xk minus 1, and so on. So I was able to obtain an equation for the, what we call the filter. And now the smoother, I come back on time. So assume that here I am consistent with all points in the past, but also all sets in the future. Then I will compute the backward reach set, and I will intersect with this one. Backward, I intersect, and so on. And I am able to obtain what I call a smoother. And at the end, I have the set of all paths that visited all sets in the right order. So just an example to finish. The Van der Pol example, I have 3 boxes, this one, and this one. And I want to find all paths that visited A, then B, and then C. So you can see here that I will draw one trajectory which show you the complexity of the problem. I start here, I go here, I may avoid it, this one, and later I may come back to C. It is why we have such a, it may correspond to a feasible path. So, of course, it's a Eulerian problem because I don't care anymore about time, but this may be zone I want to avoid. I can ask, for instance, I want to visit this one, but I want never reach B before I reach C, or I can put such Lagrangian, such Eulerian constraints, and this can be done to verify some properties of differential equations. Okay, thank you for your attention. If you have any question, I'm sorry for the end. Yes.
So when the set inclusion approach, when you're looking at differential inclusions, that's a way to model disturbances, for example.
Yes.
Now, in your application, sometimes disturbances can be bursty or like wind gusts. So it's usually, say, the disturbance is usually small, but every now and then it's very large.
Yes.
Okay. Now, to represent that, and when you do things like modeling disturbances as Gaussian, I mean Gaussian is unbounded, in fact.
Yes.
But on average, it's small.
Yes.
Now, get rid of the unbounded part. But suppose it's usually small, but every now and then it's large.
Yes.
In the set inclusion approach, you have to have a very conservative.
Yes.
So how do you? I'm sure you face that in your applications. You probably didn't. You didn't just use the larger bound.
Yes. So
if you don't use the larger bound, then you might get to infeasibility in the method. So just wondering how you try to.
Yes. So I can show you some examples, like for instance the sailboat. So it's an actual system, and excuse me. If I look at the sailboat, I can see such a thing, or such a thing maybe. So of course, we meet a submarine here. It's a large disturbance. Here we can see that it is not totally satisfied. And sometimes if I zoom in, sometimes a big wave, and the boat did this, a loop. It is not represented. But at the end, due to the fact that we had a rigorous approach, most of the time we respected the corridor. But you always have something which are not inside the model. So the bounded error approach is the set membership approach. It's a model. It is not always, the model is not always guaranteed. Because the sailboat does not obey to the differential equation. It's more complex. There is some elasticity and things like this. It's an approximation. But the fact you prove something on your system will give you a behavior which is more reliable. That's what we believe.
So you're saying it would, even when a large disturbance comes, it can disrupt.
Yes.
Guarantees, but it's very likely to recover.
Yes. So behavior is more rigorous, we can say. Yes.
So what was the bound? How large was the bound for the positions, and how is it corresponding?
For the sailboat?
Yes.
So here it's the corridor is 100 meters, 50 meters each side.
50 meters. And so how on the accuracy of the GPS?
5 meters.
5 meters.
Okay?
Another question. You said that the path should encode also information about the order of when I visited things.
Yes, yes.
But I didn't see that in the picture. So where does it come from?
Ah, okay, okay. So in maybe I went too fast on this. So in this relation, okay. Well, sorry. In this relation, I have some. So this is a set of all points that have visited all paths in the right order. So since I add the set xk after, this one will necessarily respect the order.
So it's
The
really
future.
how you compute.
Yes, yes, but
the,
okay. So yeah, maybe I went too fast, but it's not so. Okay. Yes.
You described the largest positive invariant set. It's very similar to the Lyapunov function before. Is there a relation between these two?
No. I think if you want to use a Lyapunov approach, you need a function, the function v. You need to invent by yourself a candidate for the Lyapunov function. You need intuition. Here, there is no need of intuition. It's mathematical. You don't need to add a new function coming from you.
Yeah. In both cases, was a target region that
It's similar approach. Both are Eulerian, if you want. You don't, but it's not the same. You don't have to add a Lyapunov function here. It works for any system if you want. Okay.
So you can think of it as an alternative to finding the Lyapunov function?
If you have a Lyapunov function, for instance, it's better to use a Lyapunov function in order to transform your differential problem into inequalities. Much better.
What you did here was an alternative when you don't know.
Here in this example, I don't have any Lyapunov function. I don't know. Try to find one. Normally, when we have an intuition of the problem, we can build by ourselves. Like this. For Vemos, we don't need. But for this case, no. I don't know how to find something which is similar to a Lyapunov function. There is no. We can imagine, but we don't know the equation of the cycle. I think nobody knows in the variable system the equation of the cycle. So from this, it will be difficult to find some kind of Lyapunov function which is 0 on the cycle and which provides you a distance to the cycle. Could be a Lyapunov function. The distance to the cycle. Okay? And even the distance will not be a Lyapunov function because of strange behavior, probably. Okay. So finished?
Any other questions?
Yeah?
What's the dimensionality of the flow contractor?
So we went up to dimension 3 here now. No more up to now. But the computing time for this is something like 2 seconds. So when you go to dimension 3, it's up to you can work with dimension for a few hours. Okay, so the main problem is the dimension.
So you had this function phi, which was the solution.
Yes.
Did you use that in the?
No.
Okay.
No.
So that was
Just for the definitions. Okay.
Any other
Thank-
questions? Excellent.
Thank you.
Thank you very much.
Thank you. So now it's
This is just a small gift from the university for the lecturers.
Thank you.
Thank you very much.
Thank you. Thank you.